Hello everyone, welcome back. So let's continue with the setup what we discussed last time. So we have been talking about the flexible instruments and try to understand what happens if we try to manipulate the instrument inside the endoscope, and we want to use it for robotic surgery. So if that is the case, how to proceed? So we have discussed the use and the applications, and what we wanted to have is the characterization of the tube, and when we have the input motion, what happens at the tip. So the design objective for the setup was to manipulate the instrument and from the base proximal end and its outside. So the rotation or translation we can provide to the instrument. At the same time, we also want to measure the tip motion. So what is the relationship between the input and output motion? And in between, what happens is the instrument interacts with the tissues, with the endoscope, with the access channel, what has been provided in these kind of platforms. So what is the force of interaction? Can we measure that? So we want to measure the forces as well. So these are the objectives. So we can see the instrument here and it's an endoscope. So very fine instrument we can see, and we can see the channels here. So from there it can be fed, and at the tip these instruments come out, and we can do different procedures, or we can carry out different interventions. So we started with the conceptual design, and first try to visualize what kind of setup is required and what are the different modules. So depending on that, depending on our requirement, we come up with the three modules. So one is the actuation module, so which provides the input motion to the instrument, and of course it will have the sensors encoders inbuilt, so it's there. Second is the force sensing module, so where the endoscope is mounted, and then whatever is the force of interaction that can be measured using reaction pads, or yeah, some methods we have to use, and how we can do that. And the third is the tip motion measurement module. So this is the module we are talking about, and of course we don't want to have physical contact. We want to eliminate any kind of uh, interaction which can deteriorate the performance. So we wanted to have a contactless measurement. So these are the three modules we conceptualized and started working with that. So when it comes to the actuation module, the requirements are, of course, we wanted to have translation and rotation. And okay, the translation range we define. So these are the numbers from the, like, it's after the discussion with the surgeons, and from after going through the literature, we can come up with that. So what is the range of motion? What is the resolution required? The speed at which we want to do that. So of course, for this kind of operation, we don't want to have a high speed, but slowly we want to do, and but resolution we want to have. For rotation also, the range plus minus 5 rotation might be good enough, and the resolution not very high again, and then the nominal speed, what are the numbers we are talking about. So here is not very stringent, and so what is normally required is we can stack the stages, translation and rotation, and we can directly connect it if we are not aware of degrees of freedom and constraints. But if you are exposed to these principles, very likely you are going to use it also. So it looks a normal setup, but then why not to implement some of the concept what you have studied. So for instance, if we have two stages, so one is ball screw. So we thought to use ball screw to give the linear motion. So of course the motor will rotate, and because of the pitch in the screw, if the nut is the rotation is constrained, then it will translate. So we want to use that one. So we have the axis for the ball screw, but at the same time the rotation unit or module is moving on a linear guide. So we have another axis. So we have two axes and we have to assemble. So definitely we have to take care of the misalignment and the offset. So we wanted to address that, and then based on the requirement, what we found that the requirement is just to push from the ball screw. What we want to have is this motion is given, and it will move the unit, the rotation unit, where the instrument is fixed. So only one constraint in the translation direction, what we can say. What we also wanted to have is we want to constrain the rotation of the screw nut so that it can translate, it can move it. So again, it's a screw, ball screw, the helical screw groove pattern what we have. If you look at it closely, it's only one DOF system. So the rotation and the translation is there, but then it's not independent. So for that, in order to constrain the rotation along the same direction, another constraint here, rotational constraints, and this is a translation constraint. We use the bellow flexure. So it's nothing but it's a coupling, and bellow very good. It has a very good property. So it's a stiff in rotation, but it will provide all the 5 degrees of freedom. So we use it in parallel and then build the setup. So yes, maybe if you are not aware of it, and you may find that it's very complex, but at the end what you see is very simple components, folded sheet flexure. So one sheet, metal sheet or made of SS you can take and then give a bend, and then a bellow flexure, which is simply a coupling which is used to transfer torques, that we can use and can improvise that. So we just use those two units and implement it in the design. So when we have to design this, what are the things we have to look at? So of course, for the folded sheet flexures, if we look at the design and we refer to the literature or to the lecture where we covered, what is important is what is the stiffness, and the stiffness along this direction, what is the key, and of course it's the inverse of the compliance, and the compliance is deflection is mainly because of the bending and the shear. So both are there, and then we can directly use from there. So the L is the length of the individual sheet flexures, and then E is the Young's modulus, I is the um, area moment, G and A. G is rigidity modulus, and A is the area of cross section of the sheet. So we can put it and we can calculate. So we selected the dimensions based on what is comfortable to work with, and then we try to calculate the stiffnesses and what is the offset in this case for folded sheet fractures. So we have chosen a stainless steel and probably 0.3 millimeter or 0.2 millimeter. So one can always refer to the literature. So these are all from my work, what I did during my PhD, and is everything is there in detail in my thesis and also in the paper. So we published a paper in uh, Journal of Medical Devices. So all the details are there. So you can see the stiffness is very high. It's 10 to the power 6 Newton per meter. For the bellow flexure, we have selected it from Misumi. So yeah, you can choose this from different vendors, and if it's a good vendor and is from a good source, then highly likely they will provide you the specification sheets also. So we looked at it, and the torsional stiffness we have chosen. So it has to be rigid. So 220 Newton meter per radian. So that is the number we have looked into. Of course, we also wanted to know what is the offset. So allowable offset and inclination. So this is for some life, and some conservative number we have taken it. Of course, in this case, these numbers will be not that big. So even if we are doing it manually, the offset may not be more than 0.1 millimeter, and even the inclination, these are precision linear guides. So 2 degrees is quite a big number. So it may not be that big. So this is how we work, and like if you are doing some design for precision application, I think we have to be careful. It's not just the CAD, but we have to also look at the applications and try to work with those numbers. So we got this, and then the concept we try to put in the CAD and then develop the entire setup. So it's the actuation module. What you can see is the guide, slide guide you have. So here the instrument will be mounted, and it can be translated and rotated, and it's stacked in a way, and you can see the ball screw nut here is mounted through these bellow flexures, and there will be this folded sheet flexures, so to transfer the motion. So this is implemented, and we try to make the CAD model, and this is how it looks like. So after the assembly, so you can see it takes the design effort, but after you assemble the things, it may not look that complex, and it can be, many times it can be quite obvious. One thing you have to also note down, that for assembly we use the rod, and what you can see is to fix it, we make a cut, a slit, and then try to, so we are using the flexure property to clamp it. We are not clamping directly the pin or the shaft, and there are some uh, like how to clamp the sheet flexures in order to avoid a kind of micro slip. We have to also design those clamps properly. So you can see the small edges there which is holding it. So very important. So yes, ultimately this is what we achieved. So based on the encoder's resolution, we can also find the translation resolutions, what it would be. So next is the force sensing module. So when the instrument interacts with the endoscope, what happens? What kind of forces are there? So of course we wanted to measure the force in all the three axes, and we don't expect very large forces. So maximum range is 50 Newton, and okay, dynamic range, when we like translate, slide the instrument or rotate the instrument, we can expect some variation. So of that order, and the resolution, of course we wanted to measure it precisely, so wanted to have a good resolution. We also want to have the torque measurement, so because it's rotating, so we also want to have, so in fact we want to measure all the 6 components, so 3 translation, so along the translation direction, so the forces, and along the rotation direction, if we constrain, we get the torques. So 3 torque values. So of course, what we understand after going through this kind of courses, and if we understand precisely, what we also understand that exact constraint design is the way forward whenever we have to design something for this kind of application. So we went for exact constraint design and use the method. So for instance, here you can see that at the bottom we have 1, 2 and 3. So 3 vertical rods, what we can see. So later, of course, we converted into flexure design or use the wire flexure there. But to start with, what we can always assume, you can think of constraint line approach. So it's a constraint. So 1, 2, 3, 3 constraint at the bottom. So supports the floating platform. So this is floating, and on top of this is how we are going to support the instrument or the entire endoscopic platform, so that when we are operating, then it will get transferred from the floating platform to the fixed frame through these wire flexures. So so for the time being, just assume that if these are like constraints, so 1, 2, 3 constraints from the base, so 3 constraints from the base. On the other side, 4 and 5, 2 constraints here if you see, and then 1 constraint from this side. So if we put x, y, z at the center, and this is what we at the center, these are the directions, x, y and z. So if these are the directions, what we see along the z direction, we have 3 constraints. So as we know, if we have 3 constraints in the z direction or from the bottom, it supports the floating platform and constrain it in a plane. Also, constraining in a plane means it can move only in xy plane. So the z translation is constrained, x rotation and y rotation both are constrained. So we can even talk about this. So it can move in a plane if we take 1, 2 and 3. Now if we take 4 and 5, it stops the motion along the x direction, but at the same time it also stops the rotation along the z direction. So these are something we have to visualize, and we can also visualize it from the projections. So 4, 5 will constrain the x translation and z rotation. So 3 and plus 2, 5 gone. What is left is the translation along y direction. So if we put this sixth one, it will constrain the y translation as well. So now all the 6 DOF constraint, fully constrained. So it's exactly constrained. And what we'll see that any force acting on it, or any force measured by, or any force along these lines, can give me the forces and torque values at along x, y, z, the force and the torque precisely. So whatever I have explained, that we can also check from these projections, and it also explain how the forces will be like distributed. So for instance, if there is a force along z direction, Fz, and if we assume that these all the constraints are articulated, so only it can provide constraint along the longitudinal direction. So what we will see that if there is Fz, then it will be F1 plus F2 plus F3. Yeah, plus minus we can check depending on what is the sign convention we are using. If it's a compressive load, we can say negative. If it's in tension, we can say positive. So accordingly we can do here. If force is in z direction, which is positive z direction, so it will be all tensile in along 1 2 3. So that is, if we are considering the tensile force in 1 2 3 as a positive, then we can write in this way. Similarly, Fy, if we do, Fy is only along the 6 direction, and in this case Fy will give me the compressive load on on that wire, which we can say F6. So Fz, now the is sub Fz, yeah, Fz we have already taken, Fy, Fx, sorry. So if we do Fx along the x direction, what do we see? Only 4 and 5. Here it will be negative, because positive Fx, if we apply, it will be minus F4 minus F5. So likewise we can write for moments as well. So very easy to write for mz. So mz is there, so positive direction, if it's like this, so 4 and 5, right? So yeah, means we know the distances between the two, like A and B is there, like, so just to make it different, but it can be same also depending on how we define. So mz, my and mx also we can find. So this is something one can work out and can check yourself. So when we do that and try to summarize, and what we are saying, that Fx is the bold Fx is the column vector, and it includes all the three forces and the three torque components. So Fx, Fy, Fz, and the torque component Mx, My, Mz. And Fn is the, again, these are the forces along F1, 2, 3, 4, 5, 6 along the longitudinal directions. So forces acting along the 6 wire flexures lengthwise. So if you write one by one and try to compare and try to write, we can write in a very short form, in a matrix form, Fx equal to A Fn. Fn is the force on individual wire flexures, and Fx is actually is all the 6 force components along x, y, and z. So from here also we can see Fx is nothing but minus 1, and this is the 4, so F4 and 5. 4 and 5 will give me Fx. Similarly, Fy is nothing but along 6, so the last component minus 1, so F6. Fz, xy 1 2 3, and it's the vertical direction, so it's all positive, so 1 1 1. For moments, if talking about mx, so mx is a constraint by the 2 and 3, and suppose mx is like the also 1 is along that line, so it's not off, there is no offset with the 1, but with respect to, so call it Fx. So if we talk about this, we are talking about mx and try to rotate. So these are the 2 3. So for mx, 2 and 3, 2 and 3, but one is b and one is minus b, right? So one will get compressive load, and the other will get tensile load. So that's why one is positive, and of course we have to check the nature and how is rotating. So similarly we can take my. For my is 1 and 2, 3. So 1, 2, 3, and of course one is getting compressive load, then the other two are getting tensile load. So it's a shared. For mz is the 4 and 5. So 4 and 5 you can see, and the distance, the offset is b and minus b. So one can derive it, write the equations and can get, and what you realize that this matrix, if you take the determinant of A, is non-zero. If it's 0, it means something is missing and there might be some over constraints, so some degrees of freedom left. So that also, and it also shows that for any set of one value, there is always one number. So if the forces are defined with respect to fx, fy, z and mx, my, mz, there will be one set of reading. So if I put a load cell at the bottom and measure it, I can say what are the forces acting along x, y, z and the torque values, and vice versa. So if I know what are the forces I am applying, fx, fy, z and mx, my, mz, I should know what will be the forces measured by the load cell. So it's a one-to-one correspondence, fx and that is the beauty of a deterministic design or exact constraint design is there because of this reason. There is no ambiguity. So this is one of the way. We can also try 2 to 2 configuration. So any exact constraint design we can always do. Good thing about this one is, yes, it can support, and then assembly wise is easy. If you go for 2 to 2 configuration, it might be difficult. One can also think of a Stewart platform, and we have worked on some examples, so I can show one example as well where we developed the load cell, 6-stop load cell, just using a strain gauges in and measuring in one direction, and it can be scaled up to any value. So those are the things we can develop our own and can be used and can be characterized. So this is very good, and this is the concept. Whether it works, I think we have to wait and see what are the results we got. So yes, this is the assumption, and based on that we started working and developed the CAD model. So this is how it works. So the concept is just a wire flexure, but putting a wire flexure may not be easy. So we come up with this design, and the each wire flexure is like built like this. So this is the functional part, the wire flexure what we have. So any force acting along that direction, that will be uh, the, so we have to check the load path. So it will go through that and then via the load cell, and it will go to the base, to the frame. Here you see a spring mechanism, and it's basically to safeguard if there is any extra load by accident. And many times in the university, my supervisors ask me whether it's a student proof, because yeah, people are going around and fiddling with the setup. So and somebody can easily put his hand, and the force can easily go beyond 10 newtons or 20 newtons. So what happens in that case? So that's why we put everything inside a tube, and there is a very small gap we put, and so that it should not start touching the tube. So what happens if it collapses? Then if we don't have any mechanism, safety mechanism, what will happen? this thing can buckle and it will collapse, but it will sit on the tube. So it's a hard stop. But what we did here is we develop a setup so that if it's below the critical load, the path is through outside through the tube, but moment is it increases, the preloading is smaller than the critical load. So it will simply collapse and it will go through this. So what happens in that case? It will not buckle, it will not destroy the flexure, but it will simply get deflected and sit here. So these are some of the features I think which can be easily embedded if we work on this kind of setup, and if we visualize that this can happen and how to protect our system, our setup. So this is very nice, and again how to get it and how to get that 3 plus 3 2 1 configuration with this. So this is one module. So this is what we call one dot force measurement, and this is the rendered view. You can see this load cell here, and here you have the springs inside, and here you have the wire flexure, and here you can see that 1 2 3. So the 3 are there, then 2 along this direction and 1 along this direction. So 3 plus 2 plus 1 we can get and can constrain it. Very difficult, and it's a kind of revelation also when you build it and you see that such a thin wire can hold the entire thing and there is no movement. So not very intuitive, but once you understand the constraints really well, you realize that it's enough. So this is how it looks like in the CAD and once rendered. So what are the dimensions? So many times when we do the design, yes, in CAD model things can be very good, the conceptually it looks good and we can put the numbers, but sometimes we have to also look at the functional parts. So in the entire design for sensing module, what we realize that this is the functional image, just the wire flexure is just a wire. So what would be the size, whether it's a 0.5 millimeter or 1 millimeter or 2 millimeter diameter, and what is the length? It can be 10 millimeter, 20 millimeter, 30 millimeter, right? Certain numbers we might be comfortable working with. So we may start working with that, but what happens if it doesn't work? So we have to check, we have to do some calculation. Some numbers we assume based on what is available, and some we calculate. So well, what is the basis? So if you are going for this wire flexure, and of course the if we look at the setup, only force coming on this one is either in tension or compression in the longitudinal direction. One can say what happens if this is a motion. Yeah, if there is a lateral force is coming, it will be supported by some other wire flexure, not by this. So majority, because and it will be shared depending on the stiffnesses, and that's why when we are talking about um, the directions, the constraint and degrees of freedom, basically we are looking for relative stiffness. So assuming that the forces are only in this direction, in tension is fine, but under compression what we have to be aware of is the buckling. So what is the critical load for buckling? And when we look at the setup, what we realize that yes, it's a guided, it's not simply supported or it's not free, but the both ends can just move like this if there is a small change, and this can be fixed. So under that conditions, what is the critical load? So 4 pi square, this is the number EI by L square. So this is what we are looking at. If it's a uh, a wire with a circular cross section, we can always replace with the D, and then this is the formulation. So, this is a general formulation to know the critical load. One of the thing is when you are working with these small diameters, it's very difficult to assemble. So, for that we made these slotted things here, and then you can see a slot and a hole here, and it's assembled, and a screw here, we use this screw, so threaded one, and we clamp it from there. So, these are some small features, and we have to take care of that. Next is the stress. So, how much deflection we want, and what's allowed. So, of course, we took some big numbers. So, and then suppose, so for instance, I was talking about 1 mm gap or 2 mm gap before it collapses. So, what happens if it's, so of course, the preloading is provided to prevent buckling, but what happens if it bends, if it moves, then the other flexures will bend. So, we have to allow that if we don't want to destroy the wire flexures. So, if that is the thing, so what we'll see that the deflection, lateral deflection, H versus sigma. So, maximum bending stress is also related, and the stress versus a strain relationship, and it's mainly because of the bending. So, this is one criteria. Next is the longitudinal stiffness and the lateral stiffness. Lateral stiffness is the bending, because of the bending, and this is the axial deformation, and that's why we are calling it Ka and Kb. So, along the, if this is the along the vertical direction, that's the because of the longitudinal force, and we know it's a A by L, and then we substitute A with the D, we get this formulation. For lateral stiffness is because of the bending, and for both hand fixed and moving guided. So, it's a 12 EI by LQ, and again we can have this. What happens if we compare this? Because what we wanted to know is this Ka versus this Kb, and what we are claiming that Ka is way higher than Kb, but how to ensure that? So, these are the relationship, and if we do that, what we realize that the some constant numbers, but ultimately, so we can do that pi by 4 square by L, and here E d to power 4 by L cube. So, pi cancel, E cancel, and when we do, what we find is basically, so 4 will go above 4 by 3, and then aggregate cancel, d4 here at the bottom, LQ at the denominator. In the denominator, it will go up and cancelled by 1. So, this one will be 2L square, and then here 2, it will remain here. So, it's d square. So, that's why what we are saying that this is the constant term. So, what we can say is proportional to L by d square. So, yeah, we are. So, if we just take one wire flexure, this is the ratio, and everything cancelled out except L by D and the square. So, if we have this, it's a very easy to work with. Suppose generally what we say that Ka should be maybe 1000 times Kb, yeah? So that we can comfortably say that most of the load is shared by the constant direction or Ka. So we can work with, any kind of program, or even with the actual sheet we can prepare diameter, length, critical load for buckling, allowable deflection, bending stiffness. All this, the ratio we can put, and okay, I started with 5 millimeter here to 11 millimeter here. No, it's a 0.5, 0.5 to 1.1 millimeter diameter, and for length is 9 millimeter to 41 millimeter length. And when we see that this is the some comfortable number, is we are approaching towards higher number, towards 1000, right? So among this, we thought to just select 1 mm diameter, and L is 30 millimeter here. And accordingly, what you can see, the ratio is 1200. The axial stiffness is this, and the besting is. So all this we can see here. 1.5 mm is the allowable deflection. The buckling load is also high, so 129 Newton. So we can work with these kind of numbers, and we can further develop. So it's an exploded view just to show the image, and this is how the tube can be supported on the floating platform and the instrument. And the floating platform, what is critical is this is in a way suspended on those 6 wires only, very thin wires, 1 mm and 30 millimeter with the base. And at each module, at the base, we have the load cell, so which can measure the forces in both the directions. So coming to so that is for the force measurement unit. The next is how to measure the motion at the tip, so for the translation and rotation. And for the translation, it's very easy. We can put a laser displacement sensor, what we call it LDS, and it can triangulate and we can measure. But what about the rotation? We cannot just keep rotating and measure it. So we come up with a very good solution, in my opinion, and just use the concept of a linear cam. So if it rotates, so the theta versus r, if it's varying linearly, so just thought of using that. So pi in 2 sections, so it's a butterfly kind of thing, and as it rotates, we can have this kind of configuration, and later we can stitch it and can see what is the theta, what is the rotation, and we just try to implement that. So we design a cam, and so develop it, and then through wire EDM we got the surfaces cut. So it came out very nicely, and later we'll find that the measurements are also very good. One thing is for clamping, we use again the flexure one, the side one, to clamp it to the shaft. So these are some small thing I think we have to take care. And again, here you can see that this unit can be attached to the instrument tip. It can translate and rotate, and at the same time we can measure the rotation and translation. But you also see that this bushing is air bushing, so it doesn't provide any extra friction, because the kind of friction we want to measure, or the friction forces, is very small. And suppose if we are adding any friction here, that will deteriorate the performance and it may not give us the right value. So this again worked really well. So this is how it looks like. If you look at the tip, so the instrument is connected here, and then you have the cam here, and 2 laser displacement sensors, and okay, on the other side you have, so we can take all the measurement. And this is the entire setup we have. So here we have the tube, inside we have the instrument, and the laser displacement sensor we have here, 2 laser So two laser displacement sensor here and the cam here, and again we can see the three modules. So the actuation module here can give us the translation and rotation at the same time. So using ball screw and linear slide. And here the instrument is passing through this, and what's happening, and it can be measured here. The tip motion can be measured, and all the forces, actually the below all the 6-wire flexure and load set is sitting, and it can measure and give us all the forces of interaction. So this is just one video to show. So you can see the linear cam. So at the same time we can measure the translation and rotation, and there is a this is a block where you have the air bushing, so supply pressure is there, and then there is a glass tube, and the flexible instrument is passing through. So this is sitting on top of the force sensing module, and this is what we see here at the end is the actuation module. So here you see that it was turning and also moving. So we were able to do a lot of measurement, and all the characterization, all the results is published, and is in the thesis. So you can, if you want to know the details, you can always refer to the my thesis. So from 20 is available. You can go, you can click to this DOI links, or you can also visit the IIT website and go and check my profile, and there is a freely available. Or you can also ask me. I can send a copy as well. I have some hard copies with me. The setup, the details of the setup, what I have presented is already published and is in Journal of Medical Devices. And all the details, the characterization, the measurement, although I didn't present, but all the details are there, and what kind of other measurements we performed using this setup, actually you can see. And what you also realize that these setups are later used for other application also. So it's not like it's just a kind of any ad hoc solution or a student setup. But if we put effort, what we realize that these setups can be as good as any commercial setups. And if somebody wants to develop uh, some devices or load cells or the input devices or output devices and want to sense and want to develop this thing, understanding the concept, I think is a possible to build very good setups which can be used later for other application also. So for instance, this setup later was used to test even the flight of a drone or a kite, robotic kite. So I think what one need to understand is, if you understand the principle and if you understand the kinematic design principle, exact constraint design, we can develop these tools for our own use, for medical application, for precision application, for biomechanics, for any kind of like reaction platform. This can be scaled up and can be used to measure, like we have Center for Sports Biomechanics where we are using very expensive reaction platforms. We can develop our own, or even suppose for any kind of ISO certification or any setup required by BIS to measure something in tonnage, it can be implemented. So I think it should give a confidence, and of course means after working with all these kind of setups, we should be confident to build and work on these kind of setups. So I'll stop here today, and we'll continue with the more examples and some more interesting topics from the next lecture. Thank you.